Okay, hi, I'm Chris, presenting this paper, Equilibria, Efficiency, and Inequality in Network Formation for Hiring and Opportunity. This is joint work with Cynthia Dwork, Kleinberg, and Manish. So just so we're on the same page, we're talking about professional networking today. And in professional networks, we mean the social networks for people that get into that. And decades of research has shown how important professional networks are for finding jobs, finding mentorship, all sorts of But professional networking is also, for the most part, mediated by platforms. And that means a couple of things. First, that impactful interventions on the part of platforms are not possible. So we've seen experiments with LinkedIn where they manipulate the recommendation features for the creation of new connections, and this has really big outcomes on the way that the kinds of jobs that they apply for and their income eventually. It also means that there's a lot less friction than there used to be. And so you can think about that as we go to the model. And so overall, we just want to explore the strategic behavior and networking platforms so that we can answer some questions about how we should design or regulate or rethink them so that they perform better for their users. There are a couple of different sets of questions that we investigate in the paper. So the first set is about inefficiency. What happens in equilibrium versus what a spatial planner would choose. And so that's both quantitatively and also the structure of networks that form. We also explore inequality. So how can inequality be introduced into a network that even as people into that network, there were perhaps already, or even if there were already equal. And also some investigations of what interventions a platform might make to improve efficiency in the system and what some of the challenges are there. But for the most part today, I just want to highlight some efficiency results and complete application flavor over time. Okay. So let me orient you to the model. We're going to move in two parts. First, considering a fixed network and thinking about how opportunities can occur within the network. And then we'll sort of back up and imagine how would the network form if everyone knew in advance this is how opportunities were going to be connected. So for that first part, we're going to assume everyone can use one opportunity. So you can imagine opportunities as a job or a talk or a gig. And we'll assume that some people maybe get a surplus, some people get a deficit, and in general, we'll just use this notation. Individual will get k units of surplus with probability Pi. If an individual has surplus, they'll pass their extra opportunity to those in the network or among their social contacts uniformly at random. And if you're interested, there's also an informed version of this model where people know the exogenous draws of the opportunities, and virtually everything that I'll talk about today will apply in that context as well. But it's a little bit easier to think about this like uniform at random opportunity passing, so we'll just stick with that. Okay, so on the left here, we see that in the previous slide, maybe people got some extra opportunities, they passed it to their social contact, and now this social contact has two opportunities, they can only use one. And so this opportunity, one of these opportunities gets kind of dropped on the floor. This is kind of the main source of, or the main kind of inefficiency that we'll be thinking about, which is what happens when there's non-coordination in the network as to who gets opportunities and what kinds of network structures have this happen more or less. Okay. Okay, so now let's think about how people will create connections strategically. We're going to assume their goal is to maximize the probability that they have an opportunity minus some fixed cost per A. And that no one knows what exogenous opportunities other people get, but they know the distributions of those opportunities. We're also going to assume that individuals bilaterally form connections, much like LinkedIn. Like I send a request, you have to sort of affirmatively accept it. but they unilaterally sever connections. We also need to define like an appropriate equilibrium concept for our context, right? You can imagine like we could just use a Nash equilibrium where strategies are the edges you propose, but some like trivial Nash equilibrium would be the empty network where because of this bilateral nature of connections, I can unilaterally propose some edges and improve. So Nash equilibrium doesn't really make sense here. We can think about something that generalizes stable matching. In stable matching, right, you can unilaterally sever some connections or sever a connection and form a new connection that is defect. And our context will also assume that you can't unilaterally sever connections. And if you'd be better off without a connection, then of course you can just go and click unfriend. Okay, so I want to present a couple of results today, and here's the first one. And intuitively, it just says people overconnect at equilibrium. So let's use like a simple example to illustrate why this might happen. First, let's suppose that everyone gets either one less opportunity than they need or one more than they need, and that each of these events happen with probability of time. And that no one pays for anything. So you can probably imagine just from, okay. All right, so you can probably imagine what happens when there are no hedge costs, right? It's always some chance that I benefit from a connection that I made with you and that you benefit from a connection with me, and they're free to create. So the best thing to do is just form as many edges as possible. Okay, good. So, the unique equilibrium in this, totally simple example is that the graph becomes this complete graph. Let's think about how utilities evolve. We were to choose and sort of artificially impose some other network structure. One like simple thing that we can all do in our heads, right, would be to say like, what if everyone had one connection? That is, we form a current chain. Then I flip a coin, and with probability half, I don't get an opportunity. And I flip another coin, and with probability half, you don't get an opportunity. And so, with probability quarter, if you were to get an opportunity, right, you would pass it an extra opportunity, you pass it to me. But the probability that both of those bad events happen is in the quarter, and so you can just pretty easily figure out that for this little example, the utility you get is 0.7. But you can also trace out what these different deregular graphs would look like and figure out, it's not too hard to figure out, right, that like the probability of flipping two unbiased coins and having one of them come out times is better than flipping like n coins with probability of heads like 1/2D and having one of those come heads. And so it actually would be better to form fewer connections. And you sort of monotonically decrease utilities to as everyone forms more and more connections, even though each of us, when we formed our connections, use the parallel benefits. So we can generalize this and give like a much more thorough and nearly tight characterization of what the price of energy, that is the difference between these equilibrium networks and the socially optimal ones is. And so let me orient you to the plots. The left side is when, as in the previous case, there are no edge costs. And the right side is when we vary edge costs. On the left-hand plot, we're just going to vary these two probabilities, like the probability that you get 0 opportunities and the probability that you get 2 opportunities. And you can see that it sort of lives in a simplex, and that the price of NFP is worse when both of these events get higher and that they're sort of somewhere close. On the other hand, when there are non-zero edge costs, you can sweep over the y-axis. This is connection costs, and see that for some fixed probability of getting some surplus opportunities, as you trace down through these arcs, you're switching between different feasible sets of equilibria, and so you get different price of anarchy. And actually, as you decrease edge cost in the limit, as you get close to zero, and as the surplus probability gets to zero, you get this like much higher price of anarchy. So one of the reasons that you see this like dark red corner at the bottom, this like that price of anarchy when edge costs are low and probability that anyone gets an opportunity is low, is that the low edge costs don't really deter anyone from forming a lot of connections, and they pay a cost for those connections, and so a lot of their utility gets eaten out by this overconnectivity versus versus if there were to just form a much sparser.
Can you give us a sense what those different classes on the right, like what those phase shifts look like in the actual graph that's equilibrium?
Yeah. Okay. So each one, for there to be a price of energy at all, it needs to, there need to be multiple, or there needs to be like an equilibria that is like not a perfect matching. So as you sweep down, you're going from edge costs are too high. It doesn't make sense for anyone to form a connection, either like either socially optimally, like if you're a social planner, or in equilibrium. And as you sweep down, then you switch into equilibrium where people form more and more connections. And so it's like looks like a 2 regular graph roughly, then a 3 regular graph, and so on.
The equilibrium, the agent is it's learned setup, and then no agent has any relationship. Or it's just 7.
Yeah. Right, like it's like a equilibrium version where any pair of individuals, no pair of individuals would benefit from connection,
Or removing.
or removing, or doing both simultaneously.
And it is assumed that if I want to form a connection with you, then you really want to form a connection with me, or the connection is formed only if it's something to you.
It is mutually beneficial. The second result is about the structure of these equilibrium. And so the main result here, forget about like this simple example, but we're going to just generalize out to arbitrary distributions of these opportunities and maybe heterogeneous opportunity distributions. And the result said that almost everyone is connected exclusively to others who provide approximately equal benefit. So almost everyone means a constant number of people that doesn't depend on the size of the population. And approximately equal benefit just means that the probability that you and I pass any 2 people who are connected pass some opportunity to each other is approximately equal. So again, you can get some intuition from this just in picture form. So imagine axis now that places everyone on within a fixed network on the chance that they pass another opportunity. So we can imagine these 4 people, and the top 2 people are connected, the bottom 2 people are connected. The right 2 people have a greater chance of passing an opportunity to one of their social contacts. Remember, all this is very symmetric, so like it's well defined to say that a person has a chance of passing any neighbor their opportunity. And the people on the right have a greater chance, the people on the left have a lesser chance. Of course, if this is true, and if the right and the left are far enough apart, then the people on the right would rather defect from their existing connection and form a connection with each other, right? Because they don't pay any additional edge costs. And they do benefit from this additional cost. I say that they must be far enough apart, right? Because, and like it doesn't, it doesn't matter, I guess, how far apart they are. Just like having a better probability of passing a connection is always better if you keep, this. And of course, maybe the people on the left would rather form a connection. We don't, we don't. And so that demonstrates the sort of like reciprocity that people in a large enough network can demand, right? That people in a large enough network, it may be the case that there's always someone who can provide approximately equal benefit to you. And so you never connect to someone who doesn't provide provides lesser benefit to you. And of course, if you are connected to someone with greater benefit to you, maybe they'll difference. And so you can show that this happens for almost everyone. And I just wanted to highlight, like, what is the interpretation of this? First, that we can microfound status monopoly, and so status monopoly means, of course, that like attracts like, and that people who have similar opportunity distributions may be more likely to be connected, or people who have better opportunity distributions can demand a higher chance of passing an opportunity to someone, someone that they're connected with. And this means that people enter the network and there may be even more inequality when they leave than when they enter. Okay. So just to summarize, there are two things that I presented today. One, that individuals are fully connected, and second, that they exhibit a status monopoly. Also in the paper are a couple of other different sets of questions, so we can show how there's inequality, even if everyone starts off the same. And we explore some natural interventions and discover some of these like complexities of intervening, using natural heuristics like changing the amount of friction in the system or changing the amount of information. And so that's all. Thanks.